All right, so here is the first thing that if we take a look at the practice to learn. Let's start with that. There's a couple of questions. So this 813 practice to learn is due today. 812 was due last Friday. And then I also kind of assigned a Delta Math. You're not going to get any new assignments today. It's a continuation. Keep working on 813. Try to get that in today. If you're done with that, start working on the Delta Math if you haven't done so already. And we'll go from there. Okay, so that's kind of the plan. However, there are two problems from the practice to learn that I want to go over together. One of them is problem 831. So if you take a look at problem 831 and the 831 practice to learn. Because of the fact, this probably would make perfect sense had we not skipped the first section. But because we did, there's a part in there that kind of correlates to this that made this probably a little bit harder than it would have been otherwise. This is also kind of setting up what's coming up later in the week. So that's one of the reasons why I wanted to go over this. So if you take a look at problem 831, notice it says Joey used 10 congruent triangles to create a regular decagon. So here's what's going on. Here's the idea of what's happening. So we have, let's say this triangle right there. Then if he takes that triangle and he were to rotate it just a little bit, then you've got another triangle right there. Then if you rotate it again, then you got another triangle right there. And if he keeps doing that, the idea is that he would have 10 of those to create a decagon. Okay? Does that make sense to you? That you basically are taking a decagon where this point that's right here in the middle would be like the center of your decagon. And if you took that and split it into equal triangles, you would end up with 10 of those different triangles. Okay? So the question is, what do we know about each one of those triangles? They're all congruent, but what do we know about them? And so, are those triangles, let's see where you're at on this, are those triangles scalene, isosceles, or equilateral? What do you think? Knowing that this point in the middle here is the center of the shape. What do you think? What do you think? What do your instincts tell you? Nolan, help me out here. What do your instincts tell you? What kind of triangle do you think those are? Scalene, isosceles, or equilateral? Equilateral? Okay. Why? What? Educated guess? Okay, that's fair enough. What do we think? Right or wrong on that? Equilateral? I will tell you there is one regular shape that when you split it into triangles like that, you do get an equilateral triangle. Let me guide you on this one a little bit, like I said, because you don't have the background to kind of work with it. So if you are drawing in lines to the corner points, from the center to the corner, what's happening here is, if I draw in this line, and then I go from the center to a different corner point, a different vertex, does it make sense to you that those two distances have to be the same? Because you're going from the center to a vertex? And therefore, you're just going to a different vertex, and therefore, these two pieces have to be equal to each other because you're drawing in the same segment to two different spots. Okay? And like we said, what I'm actually doing is I'm taking this triangle and rotating it over to the next one, and therefore, there's another reason why these two parts are equal to each other. Okay? Like I said, we don't know now. The one part we don't know is the bottom part right here. Okay? That's the one thing that we are not sure of. And like I said, you know that therefore it's at least isosceles. There is one specific scenario we'll talk about later on in the week where you do end up with an equilateral. So the answer here to part A is these are isosceles triangles. He is working with 10 isosceles triangles to create his decagon. Okay? So you take that and rotate it 10 different times. So then from there, if we take a look, now they ask you to find the three angle measures of one triangle. And what we're going to start with, I'll blow this up a little bit, I'm going to start with this angle right here that we're going to call, what they call these are central angles, I hope for fairly obvious reasons. It's at the center, all of those angles are at the center of whatever shape we're talking about. How do I find the measure of that angle? Let's start there. What do you think? Think about that one a little bit. Brooke?
Oh, I put 360 by 10.
Yeah, that's exactly how. So 360, if you took each one of those triangles and kept going around, then I would add that angle to it, that angle to it. Well, eventually you're going all the way around 360 degrees. And if you know you have 10 congruent triangles, you just split it equally amongst those 10. So this angle is a 36-degree angle. Okay? That's angle number 1. 36 degrees is the central angle. So then if we go through and we take a look back at that again, now how do I find the other 2 angles? How do we go about finding? Yeah, Brooke, go ahead.
180 times 36 divided by 2.
Yeah. Triangle sum. You know all 3 of them have to add up to 180. So you subtract off the 36, which leaves you with 144. And here's where the isosceles triangle comes into play. Here's why that was question A. If you know that's an isosceles triangle, then you know these 2 angles down here in the bottom have to be congruent to each other. So you take the 144 degrees that's left, and you split it equally amongst those 2. So your other 2 angles in that triangle are both 72 degrees. So you've got 36, 72, and 72 as your 3 angles. The 36 is coming from your central angle, 360 divided by however many triangles you have. And then the other ones are coming from the isosceles triangle part of things. Okay. All right, and then one other concept here for part C, which, like I said, this is gonna go directly to what we're talking about on Thursday. If they tell you the area of one of those triangles is 14.5, how do you find the area of the entire decagon? What do? Don't overthink this. Camden?
Times it by 10.
You got 10 triangles, times 10. If I know the area of one triangle, all I have to do is multiply by the fact that I have 10 congruent triangles. So 14.5 times 10 gives you a total of 145 square inches. And there is your area. That's actually exactly what we're going to be doing in 815 when we start that lesson on Thursday. That's exactly what we're going to do. It's a little bit more complicated than that. But the idea is, in order to find the area of a regular shape, work with the triangles and then multiply by however many you have. Okay? All right, so that was one problem I wanted to try to discuss. Then let's go to the back side for a second. And the other one I wanted to take a look at was problem 834. This one's a tricky problem. Mathematically, it's not hard. What is really difficult, though, is seeing how this all works. Okay? If you don't see it, it's really difficult to try to figure this out. So if you notice on 834, they talk about a quarter circle. Okay? So that's what each part is you've got a quarter of a circle. And notice the region A, is used by forming 4 quarter circles. Can you find another shape that must have the same area? So the whole problem is, can we figure out how to find the area of that shape? Which obviously we don't have no formula for, which is why we got to kind of figure out a different shape that I do know how to find the area. And that's the tricky part. Okay, so here's what I want you to take a look at. I'm going to take the top part of this shape and I'm going to cut it off. I'm going to draw a line right there. So now, if you notice above that line, I've got a half circle. And then below, you've kind of just got the pointy part of that shape. But if we think about this, there's a reason they started talking about quarter circles. If I take that half circle on the top, and I now cut it into quarters, so I'm going to cut this right down the middle. What you need to be able to notice is this. This shape right here is the exact same shape as that. If I were to go through and draw this in right here, there's a quarter circle right there. So what you can do is you can actually take that part and then move it down here instead. And then if you notice, you can actually do the exact same thing for the other part. You've got this quarter circle that you can then move to here. There's another quarter circle right there. So what you had to be able to recognize is each of those parts kind of goes diagonal to the opposite spot. And when you take all the pieces and you now put them all together, what shape do I have? There's the area I'm looking for right there. The two quarter circles plus the pointy part of it rearranged ends up being rearranged into what shape? Devin, what do you see? What shape do I have in the blue now? That's a no, all I have is a rectangle. So that shape that we started with is really just a rectangle completely rearranged is all we're looking at. So in order to find the area, we've got 14 by, what's the height? See if you recognize this one. What would the height of that rectangle be? Don't overthink this. Emily, what do you think?
7.
It is 7. Yep. And here's the reasoning behind it. Notice there's halfway, there's halfway. So this is split into 2 equal parts. So therefore, this is a 14 by 7 rectangle is what it is. And so the area of that shape is actually 98 square units. Okay, 98? I think so, yeah. So like I said, the math, 14 by 7, finding the area of a rectangle is not hard. But recognizing that that is a rectangle is very hard. That's in order to rearrange that and see it, it makes it much more difficult. Because notice what we ended up with compared to what we started with. Recognizing that that's a rectangle, like I said, is not the easiest thing. So those are the 2 problems that I wanted to kind of go over together to help you out. So now at this point, you should have at least 2 problems of your practice to learn done, and you've got the rest of them to get done to try to get that in by midnight tonight. Okay, get that in and get that in for full credit. So here's where I want to head to next. Let's go to the toolkit next. Okay, and one of the main things that we're going to take a look at, and you don't have to add anything to the toolkit or anything. I just want to highlight some of the ways that I've organized the toolkit. So if you take a look, notice at the very top, kind of notice the titles that we talked about. The upper left, this one that we're taking a look at right here. Notice I put in bold and all caps. Sum of the interior angles, okay? And specifically also any polygon. So it doesn't matter if it's a regular polygon or not. There's how you find the sum of the interior angles of any shape, whatever it is. Then if you go to the right-hand side, last Thursday we talked about the sum of the exterior angles of any shape will always add up to 360. No matter how many sides, no matter whether it's a regular shape, doesn't matter. Sum of the exterior always adds up to 360. So the top part is the sum of the interior and the sum of the exterior. Then if you take a look at the middle row here, now notice we're talking about each interior or each exterior. But one of the key parts that I want to highlight on this one is in order to use either of these formulas, you have to have a regular shape. And if you think about it, it should make some sense. Because basically all those formulas are is you're taking the sum of all the angles and then just dividing it equally. Well, I can't divide it equally if it's not a regular shape. Okay? For example, if I had some just random hexagon and all the angles are not all the same, then I can't divide it by 6 in order to get all equal angles. So that's why these 2 formulas in particular, they only work with regular shapes. Okay? And then just a couple of final things that we're going to take a look at more so today. And that is just a reminder that anytime you look at an interior angle of a polygon plus the corresponding exterior angle, those 2 are always supplementary. And a reminder again that all 4 of those formulas up at the top, anytime you see that n in a formula, n is the number of sides. Okay? So here's what I want you to do. Okay? And hopefully, like I said, you should have all of this stuff filled out from last week. So what today is, and almost tomorrow as well, is it's kind of practice of taking all this information and finding different pieces. So what I want you to do now is go to the warm-up, and I'm going to give you about 5 minutes to see if you can now take that information from your toolkit and solve these 2 problems. Okay? Solve these 2 problems. Figure out which formula to use. Basically, you're going to be setting up equations for the most part, and then solve them. One thing that I noticed, by the way, one of the last classes, is people were struggling with this idea of an n-gon right here. An n-gon is just, it means you don't know how many sides you have. Okay, that's why they call it an n-gon. Because we don't know if it's a 10-sided, 20-sided, 30-sided. We have no idea. So don't get confused by that. It's just some sided shape. And that's what you're trying to figure out. Okay, I'll give you about 5 minutes. See if you can figure these two out. Figure out which formula to use, and then go ahead and use it. Ready, go. Figure out which formula to use, then take whatever information you know and plug it in into the appropriate spot, and then try to solve for them from there. Ladies. How you doing? Everything's okay at home? Lessons okay?
Yeah.
Good. And then, unless somebody like specifically requested one, I didn't open it. I didn't start it. What you guys, how are you doing? Okay. Whatever. Generally making sense in terms of whatever. Okay. I have to have you. Yeah. Yeah. So I'll get it. Okay. Oh, first one looks good. Track doing okay? Okay, so you're on the right track here. It's not right. Okay, here's your problem right here. You just solved it. This is 180 all this stuff, right? So So instead of subtracting it over, what should I be doing? Yeah, divide those over because you're multiplying it. Then you'll be able to. Then you'll be good. Still not good. All right, let's take a look. I think most people are either done or close to it, working on the second one, almost done with the second one. If we take a look at the first problem, there's a couple of key things. When you're doing problems like this, you're looking for some key words, basically, to try to guide you a little bit. And it looked like most people were on the right track on the first one, okay? And what I mean by that is, right here, keyword number 1 is the sum. And we are looking for interior angles, okay? Or we have interior. We're working with some of the interior angles. So what I'm getting at is that if I then go to my toolkit, and basically I'm trying to figure out one of these 4. Well, the key words, once again, that's part of the reason why I put this in bold. If you're looking for some of the interior angles, you are working with this formula right up here, okay? You're working, that's how you find the sum. And the difference is, normally in the past, we know what shape we're working with. We're trying to figure out what's the sum of an octagon or a decagon. The difference this time is we know what the sum is, and we're trying to figure out what the shape is. Okay? So in this case, we can actually plug in our sum into this formula and then solve it for n. N being the number of sides again. So if we take a look, we've got 180 times n minus 2. And that sum is 2,700. Okay? We know that it equals a total of 2,700. And so now we just work our way through the algebra to figure out what n equals. 2 different ways you could have done this. Number 1, you could take that 180 and distribute. Okay? You could go through and say, let's take this 180 and distribute that into the parentheses, and then solve from there. Perfectly fine, you'll get the right answer. The other option is, because you're taking 180 times this quantity, n minus 2, you could go through and divide that 180 out right away and just get rid of it. So you don't have to distribute. Both ways will get you to the exact same answer, so it's not like there's one right way and one wrong way. It's just multiple options, okay? I'm going to go through and divide by 180 just to get it out of there. If I do that, that leaves me then with n minus 2. And 2,700 divided by 180 turns out to be 15. Well, if you remember what that 15 actually is representing then, if you go back to the formula and the way that we came up with it, remember this n minus 2 part of the formula, that's the number of triangles that you could always take a shape and cut it into. And remember, there was always 2 less triangles than number of sides. So to finish this off, we got to add that 2 back on. Meaning, we end up with n equals 17. This is a 17gon. Okay? So just a reminder, so basically in this case, you're pretty much setting up an equation and solving for the number of sides. Okay? So that's number 1. And like I said, I think most people were on the right track and doing a pretty good job at that. Okay? Number 2, again, if we start off by looking at keywords here. First, notice they tell you that this is a regular n-gon. Right away, that should take you to your toolkit of the 2 right in the middle. That's kind of why I talked about earlier, the idea of having regular shapes. Okay? Then, the second part, here's the words we're looking for. Each interior angle. So now if we go back to our toolkit, we are now focused on that box right there. Each interior angle of a regular polygon. It kind of checks all the key words. So we're working with this formula, and just like on this one, on the last one I knew the sum. On this one, I know what each angle is, and I need to figure out what's our value of n. We're going to solve it. So I'm going to take this formula and set it equal to 144. And then we'll solve from there. So, if we do that, we've got 180 times n minus 2 divided by n Again, normally that would give us each angle if we knew what shape we were dealing with. In this case, I know the answer is 144. And again, there's multiple ways you could have solved this one. Probably the easiest way that relates to what we've been doing all year is if you think of that 144 as 144 over 1, you now have a proportion. And you can cross multiply and solve it just like any other proportion we've done all year long. So if we do that, keep in mind, by the way, I'll preface what I'm about to do in all of this whole, by saying there is another way to do it that turns out it's actually a lot easier, which we'll come back to. Okay, we'll talk about that in a second. So if we cross multiply, I get 144 times n. So 144n is one diagonal. Okay, that's those two. Well, then when I multiply the other diagonal, the 1 times the 180 times n minus 2, in this case, I am going to take the 180 and distribute. Okay, so I end up with 180n minus 360. And now we're back to an equation that we can solve. Notice I've got n's on both sides, so I need to get them on the same side of the equation. We're going to subtract 180n. Move all the n's to the left-hand side. We get negative 36n equal to a negative 360. And then we finish this off. Divide both sides by a negative 36. And you find out that n equals 10. This is a decagon that we're working with. Each angle in a regular decagon turns out that it's 144 degrees. Okay. All right. Now, I told you there's a different way to do this. So let's kind of work back. Jackson, I'm going to come to you, because I know you explained it to me already. You explained the other way of doing this, so I'm going to come to you. What did you do? You didn't do all this work. What did you do instead? Okay, so what Jackson recognized right away was if each interior angle is 144, well, don't forget, right here, each interior and exterior angle add up to 180 degrees, which means the exterior angle then happens to be 36 degrees. And we know that the sum of all the exterior angles, no matter what shape I'm dealing with, is 360. So if we take the total of 360 degrees, and if each angle is 36, I can divide by 36, and that'll tell me how many angles I have, which in this case is 10. Notice you get the exact same answer. Okay? So, and that's one of the reasons why that box is on your toolkit. That's one of the reasons why I had you put it there as its own separate box. Because when you're doing problems like this, sometimes it's easier to do the interior, which is exactly what they give you. Sometimes it's easier to use the interior to find the exterior, and then do it that way instead. Okay? So it's more of a reminder that, hey, don't forget, you've got both options when we're dealing with interior and exterior angles. Okay? Anybody have any questions on that? Like I said, that method is a whole lot quicker and easier if you recognized it. Okay? If not, it's okay. You get to the same answer the other way. Okay, so here's what I want you to do then. And it's totally up to you if you want this right in front of you or not. But if you take your warm-up and flip it over, on the back side, I'm going to have you do some practice problems. This is just the last problem of the lesson from 813. So if you want this directly in front of you rather than just up on the screen, you're welcome to go ahead and log into the ebook, go to lesson 813, bring this up. So you've got it right there for you. Otherwise, what I want you to do, again, I'm going to give you about another 5 to 7 minutes. I want you to now that you've seen a few of these types of problems, work your way through parts A, B, C, and D and answer those questions. Again, just practicing what we were kind of working on here. All right, let's see what you got. If you get stuck, ask. And I will, like I said, I'll come and help you out. I'll guide you a little bit. And you can just do them right on the back side of the warm-up. Use your toolkit to help you out. Again, look for those keywords. Are we talking about a sum, or are we talking about each angle? Are we talking about interior, or are we talking about exterior? Those are kind of your keywords that you're looking for. Regular polygon, or does it not matter? And again, if you get stuck, please ask. The worst thing you can do is sit there and do nothing. You'll be totally lost. What are we doing here? Yeah. Good. There's one lesson where one slide there, basically. But so I can find that. It's called a polygon. All right, let's take a look, see what we came up with here. Hopefully the first couple were fairly straightforward because they're very similar to what we did in the warm-up. So if you take a look at part A, notice, again, I'm going to kind of highlight those key words that give you ideas of how to do each problem. So notice Gerardo drew a regular polygon There's a key word right there. That should narrow everything down on your toolkit to 2 boxes. Regular polygons dealing with interior or exterior angles. Okay? Which then leads you to the next part. We are talking about exterior angles. This one is very, very similar to like what Jackson was telling us before. Okay? If you know that one exterior angle is 40 degrees, and you have a regular polygon, you know that the sum of all of their exterior angles is 360, and therefore you can just divide 360 by 40 to figure out how many angles you actually have to get to 360. So in this case, you end up with 9, and therefore this is a nonagon. And you have a regular nonagon, 9-sided shape that you're dealing with. Again, not the only way that you could have done it, but probably the quickest and most efficient way to do it. Okay? Part B is pretty much the exact same idea as what we did on the warm-up. The only difference is instead of the sum totaling 2,700, now the sum totals 2,520. Okay? So you should know right off the top that since we had 2,700 was a 17-gon, you should know right away, hopefully, that it's less than 17 sides just based on that information. Okay? But otherwise, it's exactly the same process. 180 times n minus 2. Keywords again, interior angle sum. That leads us to this formula. And we know that the sum is 2,520. And then we can solve for how many sides does it take to get to that sum. So divide both sides by 180. Therefore, n minus 2 will equal, this is 14. And then you add the 2 over, and therefore, this is a 16-gon is what you should end up with for that one. And so A and B, like I said, very, very similar to what you had in the warm-up, just kind of working your way through it again. How about part C? We've got a quadrilateral with 4 sides. What's the measure of each interior angle? What'd you come up with on this one? What'd you do? Braylon, help me out. What'd you do on this one? Okay, yeah, so key parts here. We've got each interior angle, okay, and we know that this is a quadrilateral, which therefore tells me I've got 4 sides. So in this case, if I'm looking for each angle, and I know it's a quadrilateral, I know what n equals, and I'm trying to find each one. So if we go through and we do that, we've got 180. Instead of n minus 2, I can plug in 4, because I know I've got 4 sides. That'll give me the sum. And when I evaluate that, remember when you're evaluating, think of your order of operations. Do the stuff in parentheses first. So 4 minus 2 gives you 2, times 180, gives you a total of 360. And then we're going to divide that by 4, and you got an answer of 90 degrees, right? The reason that this is here, this problem is a trick question. And I'm not sure, did anybody catch it? This problem is specifically here to see if you would catch the trick. It is not 90 degrees. Anybody tell me why? I'll give you a hint. What's wrong with what I did? It's very, very subtle, but it's very important, which is why this is in here. What word is missing? What is it? Regular. This just says that we've got a quadrilateral. Remember, if we're going to use this formula right here, where I'm going to take the total and I'm going to divide it equally amongst the 4 angles, you can only divide it equally if you know that all 4 angles are the same. And unfortunately, all they told me was this is some random quadrilateral. They did not tell you it was a regular quadrilateral. So I don't know for sure that all 4 angles are equal. The actual answer to this question is, I have no idea. I don't have enough information to answer it. Okay? Because this might be a kite. This might be a rhombus. This might be a trapezoid. We don't have any idea. And because of that fact, I know the total has to be 360 because it's quadrilateral, but I don't know what each angle is unless it's a regular shape. Okay? Does that make sense to you? The idea behind that? like I said, it was a full-on setup to see if you would go through, and I didn't notice anybody that caught it, which is fine. That's why we're talking about it together. Okay. And then finally, last one, part D here. As you take a look at this one, I asked you, what's the measure of an? Here's again keywords. An meaning one. Interior angle. Okay. If you have a regular, there's another keyword, 360 gon. So a couple of different ways that we could do this. Sometimes it's easier to go through and use the interior angles and find it directly. Sometimes it's easier to use the exterior angles. I'm going to do the exterior one first. What's the measure of each exterior angle on this one? If you have a 360 gon, each exterior angle would equal what degree? Yeah, Kevin? 1. You know the total is 360 degrees, and you have 360 angles, so therefore each exterior angle would be 1 degree. But what I'm looking for is each interior angle. So therefore, what's the measure of each interior angle? Oh, there you go. 179. Because remember, interior and exterior are always supplementary to each other, so each interior angle would be 179 degrees. Again, it's not the only way you could do it. We could have found it directly using the formula if we needed to. But, which by the way, if you think about that for a second, if we have 360 sides and each angle is 179 degrees, that means we have something like this. I'm just going to kind of sketch this out. Let's say there's one angle, and then if we go through and maybe there's another angle, and then here's another one, something like that. What shape am I basically drawing? Yeah, we're basically drawing a circle. We're really, really, really close to probably having a circle. And that, again, that's kind of the layout of this whole chapter, is if we just keep adding sides, we're getting closer and closer and closer to a circle, which is what we're going to end the chapter with. All right, here's where you're at for assignments. I kind of mentioned it at the beginning. 812 assignment was due last Friday. If you don't have that done yet, get that done and get it turned in. 813 is due today. We did 2 of the problems together. Okay, so hopefully now you can just do the rest. And then reminder, you have everything you need to know in order to do the Delta math as well. So if you have not started the one that I assigned last week, you can start working on that and get that done by the end of the week. That's all I've got for you today. We'll move on tomorrow. Have a good rest of your Monday.